It begins in myth. Nearly 3,000 years ago, the gates of Olympus opened on their own. In Homer's tale, the god Hephaestus forged golden servants, statues that could walk, speak, and think. To the ancients, these were stories. To us, they look like something else, the first blueprint for artificial life. For centuries, the dream persisted. Talking brass heads in medieval monasteries, clockwork dolls in royal courts, metal made to mimic life. Again and again, the same question returned. Can intelligence be built? Back then, it was fantasy. Today, it is real. Artificial intelligence is not a modern invention. It is the continuation of one of humanity's oldest dreams. And like every dream, it carries a shadow. The dream of artificial life moved from myth into mathematics. In the 1600s, Gottfried Wilhelm built a machine of brass and gears, the step reckoner. A calculator that could add, subtract, multiply, divide. But Gottfried imagined more than arithmetic. He dreamed of a universal language, where every thought could be reduced to symbols, and reason itself carried out by calculation. For every human activity, he believed, there could be a mechanical counterpart. It was audacious, the first vision that logic itself could be automated. 2 centuries later, the quest accelerated. Charles Babbage, an English inventor, designed engines of steam and steel. His difference engine, in the 1820s, promised to automate mathematics. By 1837, he imagined something even greater, the analytical engine. It had memory, a processor, a mill, even punch cards for programs, a Victorian computer that foreshadowed everything to come. By his side, Ada Lovelace saw deeper. In 1843, she wrote of the engine's limits. It can do whatever we know how to order it to perform, but it has no pretensions to originate anything. A machine, she warned, could follow instructions brilliantly, but could it ever think for itself? The question lingered. For a century, it waited in silence. Until a young mathematician named Alan Turing would take it up and change the world. Fast forward to the 20th century. World War II rages. Amid the whir of electromechanical computers, a quiet revolution begins. Alan Turing, a young British mathematician who bridged theory and imagination. In 1936, Turing described an abstract machine, a thought experiment, a Turing machine. It proved something astonishing. Any process that could be described as an algorithm could be simulated by a machine. Universal computation, the foundation for every digital brain to come. War gave the theory urgency. In the 1940s, the first programmable digital computers emerged, machines of wires and switches, but beneath them, Turing's vision, a universal mind made of logic. Turing believed in that possibility. He saw no gap between the brain and the computer. A machine of sufficient complexity, he argued, might evolve behaviors never explicitly programmed. A machine that could surprise us, create, imagine, think. In 1950, he reframed the question, not, can machines think? Too vague, too loaded. Instead, the imitation game. Today we call it the Turing test. The setup: a judge types to 2 hidden entities, one human, one machine. If the machine can fool the judge as often as the human can, then what reason do we have to deny it intelligence? The shift was profound. Intelligence was no longer about definitions, it was about performance. If it talks like a mind, who's to say it isn't one? Turing predicted that by the year 2000, machines might pass the test. That milestone hadn't arrived, but his challenge lit a fire. It became a clarion call. Build machines that think. Let their behavior speak for itself. The race was on, and today, AI is everywhere, which makes it the perfect time to mention our sponsor. These days, AI tools are everywhere, and buying them individually, it adds up fast. That's where RouteLLM.Abacus.ai comes in, a unified platform where all the leading language models are available in one place. You get access to ChatGPT 5, Claude Sonnet 4.1, Gemini 2.5 Pro, Grok 4, DeepSeek and others, with RouteLLM smartly choosing the best model for each prompt. It's not just text generation. You can create images using Flux, Ideogram, Recraft, or ChatGPT's image model, and generate videos with tools like Kling, Runway, and Halo, all from simple prompts. There's a humanize feature that rewrites AI text to sound more natural and bypass detectors. You can even vibe code websites and apps and create full presentations, research reports, or build complete apps using Deep Agent. And for coders, it includes CodeLLM, an AI coding editor built right in. All this for just $10 a month. Visit RouteLLM.Abacus.ai or click the link in the description to explore it now. Now let's back to the story. The mid-1950s. Science fiction dreams, Cold War anxieties. And in the middle of it all, a new idea pulling brilliant minds together. The summer of 1956, Dartmouth College, a small workshop that would become ground zero for artificial intelligence. John McCarthy, the young mathematician who coined the phrase artificial intelligence, alongside Marvin Minsky, Claude Shannon, Alan Newell, Herbert Simon, They came with a bold proposal: machines could simulate every aspect of human intelligence. Imagine the scene: a handful of pioneers gathered under the New Hampshire elms, sketching futures on blackboards, arguing, dreaming, programs that could use language, solve problems, improve themselves. During those weeks, Newell and Simon revealed their breakthrough, Logic Theorist, a software program that could prove theorems in symbolic logic, even finding an elegant proof that had escaped Whitehead and Russell. A thinking machine. Concrete evidence that computers could manipulate symbols, the very stuff of reasoning itself. By the end of the workshop, optimism soared, perhaps too high. Many believed human-level intelligence was only decades away. Artificial intelligence was officially born. Declared in the conjecture, every aspect of learning, or any other feature of intelligence, can be so precisely described that a machine can be made to simulate it. A plaque now marks the spot in Dartmouth's Baker Library, the place where a new discipline began, the place where a handful of adventurers set sail on uncharted seas of the mind. The 1960s. AI labs spring up at MIT, Stanford, Carnegie Mellon, fueled by optimism, fueled by government grants. Early triumphs arrive. Programs solve algebra word problems, prove geometric theorems, even speak in limited ways. At MIT, a program called Eliza shocks the public, a text-based therapist mimicking human conversation through simple pattern matching. Newell and Simon's general problem solver tries to replicate human strategies of reasoning. At SRI, a robot named Shaky navigates rooms, stacking blocks, guided by logical planning. It feels as if human-like AI is just over the horizon. But shadows gather. Common sense, vision, language. These problems prove far harder than anyone imagined. By the late 1960s, cracks appear in the optimism. One blow comes from within. In 1957, Frank Rosenblatt introduced the perceptron, a machine inspired by the brain's neurons. It could learn to recognize patterns. The world greeted it as a breakthrough in machine learning. But in 1969, Marvin Minsky and Seymour Papert published perceptrons. Their verdict was damning. Neural nets, they showed, had strict limits. A perceptron couldn't even solve the simplest logical problem, XOR. The dream of learning machines collapsed. Funding for neural networks dried up. Symbolic AI took the stage, and connectionism was declared a dead end. Then came the harshest blow of all. 1973, the Lighthill Report. Commissioned by the British government, it delivered a brutal judgment. AI had failed to meet its promises. No general-purpose intelligence was in sight. Overnight, funding was slashed. Entire labs shuttered. In the US, DARPA lost patience, redirecting resources to more immediate military projects. The momentum drained away. It became known as the first AI winter. Paradise lost. Scientists who once predicted human-level AI within a generation admitted their mistake. John McCarthy himself reflected, the problem of intelligence was far harder than they had thought. The dream did not vanish, but it was put on ice. AI survived only in small niches, puzzle solvers, chess programs. The broad vision slipped beyond reach. The epic was entering its first great setback. Every winter gives way to spring. By the early 1980s, AI found new momentum. Not by imitating the general mind, but by capturing fragments of expert knowledge. The heroes of this era were expert systems, programs built to mimic specialists in narrow domains, doctors, geologists, engineers. Instead of creating a genius from nothing, why not encode the wisdom of human experts into machines? Governments and companies rushed to invest. In Britain, the ALVI program poured millions into computing research. Paradise regained after the bleak 1970s. In Japan, the fifth-generation computer project aimed to leap ahead of the West. The US responded in kind. Once again, AI was heating up. At Stanford, one project showed the way: Mycin, a medical program that diagnosed blood infections. Within its narrow scope, it performed as well as physicians. Its secret, a knowledge base of hundreds of IF-then rules, the distilled expertise of real doctors. The formula seemed simple: knowledge is power. By the mid-1980s, expert systems were everywhere. Prospector for mineral exploration. XCon at DAC, configuring complex computer orders. Systems for credit checks. Factory troubleshooting. One survey counted more than 130 expert systems in daily use across industries. Money flowed. Careers were made. Wall Street caught the fever. Companies like Technology and Intellicorp went public, promising to bring AI to the masses. The media proclaimed the rise of the expert company. It looked like a royal road to machine intelligence. Not through learning, not through reasoning, but through encoded expertise. But as before, hype raced ahead of reality. Each system was brittle. A specialist, yes, but helpless outside its narrow task. Maintaining the knowledge bases was slow, costly, error-prone. Clients discovered that simpler software often worked just as well. By the late 1980s, the market soured. AI companies folded or were acquired. Funding evaporated, and the second AI winter descended in the early 1990s. Once hailed as the next big thing, expert systems faded quietly into history, just another kind of software. The pattern was now familiar: feverish progress, cold disillusion. But every failure carried a lesson. From the 80s boom, one truth became clear: knowledge alone was not enough. True intelligence needed something more flexible than rules. A new idea was stirring. What if machines didn't just store knowledge? What if they could learn it for themselves? Out of the ashes of expert systems, a new paradigm emerged. Not rules, not hand-coded knowledge, but statistics, data, self-improvement. This was the rise of machine learning. Instead of telling a computer how to solve a problem, engineers fed it data. The machine would find patterns on its own. Anil Ananthaswamy put it simply: machines that discern patterns in data without being explicitly programmed to do so. In the 1990s and 2000s, this approach quietly reshaped AI. Neural networks revived in new forms. Decision trees, Bayesian models, support vector machines. Algorithms that learned from examples and improved the more data they consumed. Intelligence, not written line by line, but grown from data. Then came the spectacle. 1997. A 6-game chess match shook the world. IBM's Deep Blue versus Garry Kasparov, the world champion. The machine won. Kasparov, humiliated, admitted he had seen deep intelligence and creativity in its play. In truth, Deep Blue was no genius. It examined 200 million positions a second, armed with handcrafted heuristics. It wasn't learning, it wasn't general intelligence. But symbolically, a fortress had fallen. If a machine could defeat the best human in chess, what next? Meanwhile, quieter revolutions spread. Speech recognition moved from novelty to practicality. Systems like Dragon Naturally Speaking, trained on massive datasets, could now transcribe with striking accuracy. In computer vision, researchers abandoned hand-coded features. Machines began learning directly from thousands of labeled images. Robotics embraced probability, allowing robots to localize and move through uncertain worlds. AI was shifting from pre-programmed smarts to adaptive systems that improved with experience. Through the 1990s, neural networks survived in the margins. In 1986, backpropagation had resurrected them, making deep multi-layer networks possible, but progress was slow. On most tasks, simpler methods still won. Still, a small band of pioneers, Geoffrey Hinton, Yann LeCun, Yoshua Bengio, kept the dream alive. They believed deep networks held hidden potential, that one day, with more data and faster machines, these models would reveal their true power. By the dawn of the millennium, the world was changing. Moore's law was accelerating. The internet was flooding the world with data. The stage was set. Connectionism, once dismissed, was about to return. And this time, it would reshape everything. The 2010s. Artificial intelligence breaks through. Not slowly, not quietly, but in a cascade of triumphs that redefine the field. This was the era of deep learning. Multi-layer neural networks, billions of connections, fueled by massive datasets, powered by GPUs. And suddenly, they worked. 2012. AlexNet. A deep network entered the ImageNet competition, a global benchmark for object recognition. It crushed the field, error rates cut in half. The message was undeniable: bigger networks, more data, more compute, meant better performance. After decades of winter, AI had found its engine. And its fuel. The takeoff had begun. The breakthroughs cascaded. Machines could see, labeling photos, recognizing faces, describing scenes. They could hear and speak. Voice assistants like Siri and Alexa moved from gimmick to ubiquity. And then came the game of Go. 2016. Seoul. Google DeepMind's AlphaGo faced Lee Sedol, one of the greatest champions of all time. Go had long been seen as a last human stronghold. Experts thought mastery was decades away. AlphaGo won, 4 games to 1. Sedol's expression told the story: confidence, confusion, shock. Game 2, Move 37. A move so unorthodox that masters called it genius. It wasn't brute force. It wasn't rote calculation. It felt like intuition. For the first time, a machine revealed an alien kind of creativity. And then language. By the late 2010s and early 2020s, enormous neural networks trained on trillions of words began to write, to converse, to explain. ChatGPT arrived in 2023. A free demo. Suddenly, anyone could chat with an AI that drafted essays, wrote code, even cracked jokes. What had felt like science fiction only years before was now in a browser tab. Momentum exploded. Every week brought a new headline. AI composes music, discovers antibiotics, creates art from text. Cars drive themselves, haltingly. Doctors use AI to spot cancers in scans. These systems are flawed, imperfect, sometimes dangerously so. But their trajectory is undeniable. The more data, the more compute, the better they become. Even their creators watch with astonishment. For the first time, people outside the tech world felt it. The sense that machines were reaching into territory once thought ours alone. Creativity, intuition, conversation. The line between understanding and imitation blurred. And AI stepped out of the lab, into everyday life. And so here we stand. The mid-2020s, at once thrilling, at once precarious, the dream of artificial intelligence has, in many ways, come true. Machines now perform feats that dazzle. But the tension has shifted. It is no longer whether we can build them. It is how we will live with them. One concern is trust. AI systems shape daily life, recommending news, screening job applications, guiding cars, advising courts. But how much should we trust their opaque decisions? Sociologist Helga Nowotny calls it a paradox. We turn to algorithms to reduce uncertainty about the future, forgetting they are built on the past. And the more we trust their predictions, the more we may act to fulfill them. Self-fulfilling prophecies. Agency, quietly slipping away. The GPS that leads drivers astray. The policing algorithm that reinforces its own bias. Perhaps the deepest worry is alignment, ensuring that an AI's goals remain in sync with our values. What happens if they do not? A recommender trained to maximize clicks may manipulate attention. A superintelligence with an ill-specified goal might pursue it with devastating efficiency. Stephen Hawking warned that advanced AI could be either the best or the worst thing ever to happen to humanity. Stuart Russell puts it more starkly. Pursuing ever more powerful AI without solving the control problem, he argues, is a game with one possible payoff, minus infinity. An unaligned intelligence might wipe out its creators, not from hatred, but from indifference. Not a villain, but a blind god. What was once science fiction is now a serious subject of research papers and policy debates. In response, the AI community races for safety. Russell and colleagues propose a new paradigm, AI designed to remain uncertain about human values, always seeking guidance, always deferring. Not an autonomous agent with fixed goals, but a system that knows it doesn't fully know what humans want. Meanwhile, ethicists and policymakers draft frameworks, transparency, fairness, accountability, dozens of guidelines circulate. But consensus is elusive, cultures differ, stakeholders disagree. And the hardest dilemmas, a self-driving car choosing between two harms, refuse to be reduced to code. Ethics is necessary, but not sufficient. The quest for AI safety is no longer just technical. It is social, philosophical, global. The challenge now belongs to all of us. Looking back, the history of artificial intelligence reads like a saga. It began with ancient dreams, mechanical servants of gods, golden automata moving in myth. Then came the Enlightenment calculators, the Victorian clockwork brains, the visionaries like Alan Turing, imagining machines that might rival human thought, and the cycles of fortune, the early triumphs, the long winters, the revivals and renaissances. Each chapter left its mark. Symbolic reasoning, neural nets, expert systems, machine learning, deep learning, layer upon layer, like the networks we build today. And now, we are inside the story. AI is no longer confined to labs or law. It is everywhere, in pockets, in workplaces, in homes. This reflection, this very film, is part of the narrative. But the ending is unwritten. Helga Nowotny reminds us, the co-evolutionary journey between humans and digital machines has only begun. AI reflects us, our values, our biases, our hopes. We stand at a crossroads. We can guide it for the common good, or let it drift toward outcomes we may regret. Perhaps the deepest lesson is not about machines at all. In teaching them to think, we are forced to ask what thinking means to us. In building artificial minds, we hold up a mirror to our own. The final image returns to the machine. A chess engine, calculating victory. A server farm, lights blinking in patterns of alien cognition. A robot arm sorting recyclables with uncanny grace. In that reflection, we see both promise and peril. The choice is ours. Will these creations remain our tools, become our collaborators, or confront us in ways we cannot yet imagine? The quest continues, unfinished, open-ended. A grand narrative of minds and machines, together seeking to unravel the mystery of intelligence.